Swayam Prabha. Digital India. Educated India.
Hello friends, welcome back to the second lecture of our second week where we are talking about the response of different measurement systems. If you remember our discussion from the previous week, I am sure you remember that. There we have talked about the characteristics of a measurement system, and primarily there are two kinds of classifications we get. One is the static characteristics where we talk about both time invariant input and output. That means neither of the input and output changes with time, both are perfectly under steady state condition. So then whatever we get, that we call the static characteristics. Common static characteristics we have already discussed last week, like sensitivity, linearity, zero bias, resolution, then drift, hysteresis, etc. different kinds of static sensitivity, or I should say static characteristics, not sensitivity. We have already seen different examples of each of those characteristics, and also from some given information how to harness information about each of the static characteristics. Some of the exercises we have also done. I am sure you have done the assignments also where similar questions are there. Now one question that may be popping up in your mind, that we are talking about both input and output to be time invariant, and the very common perception there may be, if the input is a steady one, that is it is not varying with time, then you can expect the output from your measurement system also to be time invariant. And then why you need to mention both input and output separately? The answer to this question is that it may be possible, even if your input is under steady state time invariant, your output, that is the output that you are going to get from your measurement system, may keep on varying with time, and we shall shortly be seeing a few examples right in this particular lecture. And therefore, to ensure the static characteristic, both input and output needs to be time invariant, and then only we can talk about those characteristics like sensitivity and linearity and resolution, etc. However, when the both of them are varying with time, or at least the output is varying with time, we talk about the dynamic characteristic. And in this week's content, we are primarily talking about the dynamic response of a system. And some of such characteristics we have already discussed in the previous lecture, where we focused quite a bit on different kinds of inputs, particularly the time varying inputs in the form of periodic function. We know that whenever we are dealing with a periodic function, however complicated it may be, using the Fourier transform we can always convert that to a series of or a summation of a series of sine and cosines, and from there we can easily identify the amplitude and frequency, and if there is any phase lag at all for each of those components, and we can represent them either as a time signature or in terms of the frequency spectrum, etc. And when that kind of input signal, periodic or sometimes maybe time varying but non-periodic signals are imposed on measurement system, of course the output is also going to be varying with time. And whenever such kind of periodic signals particularly we are talking about, there are several very common dynamic characteristics that we have to be careful of, like the amplitude response, phase response and frequency response, which are the most common to be used. So today's lecture we are going to discuss about zeroth and first order measurement system and its response to certain standard input signals. Now in towards the end of the last lecture, I started developing the mathematical model of a general measurement system, but because of the paucity of time I had to quit very early, and so I shall be starting that one from fresh. We have got the idea that the purpose of a measurement system or the operation of a measurement system can be viewed to be like a mathematical operation being performed on the input to get some output. Like as shown in this slide, if x is the input that is given to the measurement system, we can view the system to be performing some kind of mathematical operation to give us an output as y. And of course, here we are restricting ourselves to single input single output systems. It is possible for the same system to have multiple inputs and have multiple outputs, but that will be too complicated to discuss in a course like this. So, we are restricting ourselves to a single input which is denoted as x, and a single output which is denoted as y. Then the most common relation between this x and y in terms of differential equation can be formed like this, where the left hand side corresponds to the input, or sorry, corresponds to the output, where we have the y. Here a naught, a1, a2, all these are the coefficients, and this n, or maybe this n, this is generally referred as the order of the system. Whereas on the right hand side we have the input part in terms of x. Here again we have several coefficients b naught, b1, b2, etc. up to m. N and m may be same or may be different, but both are integer numbers. Order of the system, I repeat, is given by the n and not by m. So, order of the system we refer in terms of this n, and when n is equal to 0 we call that a zeroth order system, when n equal to 1 we call it a first order system, and it goes on that way. Now, quite commonly in mathematics or any such kind of system analysis, instead of using the differential notation which is ddt here, we like to represent this in terms of an operator capital D. So, if you introduce that capital D operator, it looks quite similar to an algebraic equation, but be careful here, D is not any algebraic quantity, rather it is just an operator, the differential operator. So, this is the equation or relationship between y and x in terms of this operator D. And so, again drawing analogy to the algebra, we can represent them in a form like this, where the numerator contains the coefficients associated with the output and denominator contains the coefficient associated with the input. Here we are getting then a ratio of the output to that of the input, to the input. Both may be time varying, may be time invariant, but here our importance or our focus is more on this right hand side, which is giving this ratio of output to input. Quite often here, when we are dealing with a higher order equation, that is n is higher than n is a high value, or n has a large magnitude, then dealing with such ordinary differential equation may be quite complicated. And that is why quite often for solving such equations, instead of directly solving that in the time domain, we prefer to perform a Laplace transform, so that instead of using this time t as the independent variable, we get that to convert it to s, which is the frequency domain parameter. S is the frequency, which is actually a complex number, and using the Laplace transform we can get this conversion from this independent variable time to the independent variable frequency. And I have already asked you last week itself to take a look at Laplace transform, just revise your Laplace transform exercises, and from that knowledge we know that the differentials can be directly related to S using the Laplace transform to have a form like this, where all these D operators can directly be replaced with this S to get a very similar algebraic operation like this. The advantage of this Laplace transform is that the ordinary differential equation that we have here with time as the independent variable gets converted to an algebraic equation with S as the primary variable, and hence we get this particular thing where input capital X is the Laplace transform version of the small x input small x, and capital Y is the again the output represented in the frequency domain, and in between we have the mathematical operator which is being performed on x to get y. This mathematical operator we often refer to as the transfer function. G is one of the common way of representing this, but there are several other ways also we represent this transfer function. So, this concept of transfer function is a very important one in this topic of measurement system. Some of you may have already gone through some course of control systems, and their similar treatment you have already found. Actually, if you have already done control systems, the entire content of this week you may be very much familiar with. But the idea of transfer function is to represent the entire mathematical operation performed by this measurement system in terms of a single operator, which is this transfer function, and once we know the transfer function of one instrument, then we can very easily relate the input and output by performing corresponding mathematical manipulations. And even bigger advantage is that when we have multiple instruments or multiple components to deal with during a measurement, using these operators we can easily connect different components to get an equivalent transfer function. Let us see an example here. Here we have an example of a quite complicated measurement system, or where we are using series of operations. Here R refers to the input, Y refers to the output. Let us just instead of using R, let us just stick to our original notation X. So, X is the input, Y is the output, and here there are several operations being performed. Like here we have several instruments having their transfer functions as G1, G2, G4, etc. There are different components. Also you can say there are 3 H1, H2 and H3, 3 components which refers to feedback. I am sure you have some idea about feedback, which are primarily used for control operations. Like here whatever variable value that you have here, that is being proceed to G5 towards the component having transfer function as G5, but also that same signal is being routed through this particular feedback component to get back to the original input position, which returns which gives at this particular point, instead of supplying the original signal X, if there was no feedback the original signal would have been X, but here as we are supplying something, then the original signal will be X plus H2 times if whatever we have here. Suppose if at this particular point our variable value is X1, then it will be H2 times X1. This is the signal that is coming to this particular portion through this line. And then we are having another feedback here. If the value of the signal at this particular point is X2, then whatever being transferred here is X plus H2 X1, which was already coming, plus this H1 X2. This is the signal that is reaching this particular component. This is the idea of feedback, and so using these components we can easily calculate the corresponding transformations. Now there are several components. If we count properly, we can see there are 5 plus 3, total 8 components involved, each of them having its own transfer function. So somehow we have to combine them. That combination process can be very easy. There are generally 3 kinds of possibilities we get. First possibility, let me erase it to make it a bit cleaner. First possibility is where we have 2 components connect in series. Connect in series means the output from the first component is directly fed to the second component. Like if the first one is having output G1, second one is having, first one is having transfer function G1, second one is having transfer function G2, and let us say X1 is the signal that is being fed to G1, its output is X2, then this output is directly fed as an input to the component having transfer function of G2 and giving a final output as X3. Then how can we calculate? Using the notations that we have for the first component, we know that output upon input, if that is X2 upon X1 will be equal to G1, which is giving X2 is equal to G1X. Now look at the second component. Output from the second component is X3. What is the input that we are giving? That is G1 into X, and that leads to our output as G1X1. So that leads to our output as X3. Output, I repeat, output from the second instrument is X3 and its input is G1X1. That will be equal to the corresponding transfer function, which is G2, which gives X3 is equal to G1 G2 X1. Hence X3 upon X1 is equal to G1 G2, which is the combined transfer function of these 2 components. That means when 2 or more components are connected in series, their equivalent transfer function will be a product of their individual transfer function. We can see one such arrangement here in this case. So this is possibility number 1. Let us move to the second possibility. Second possibility is when the components are connected in parallel. Parallel means where they are not being subjected to same inputs, rather something like here, their both ends are connected to the same point, something like say if x is the net output that you net input that you are supplying, a component of x which is x1 is going to the first component having transfer function g1, and the remaining portion that is x2 is going to the component having transfer function g2. So, from the first component we are getting an output y1, from the second one we are getting an output y2, which is giving us the net output y. Now, we can easily see that x will be equal to x1 plus x2. Now, what will be the relation between x1 and y1? Using the definition of transfer function, we know y1 upon x1 will be equal to g1 and y2 upon x2 will be equal to g2. Hence, y, which is y1 plus y2, that will be equal to g1 x1 plus g2 x2. So, this is the net output that we are going to get, and if our interest is to get the net transfer function or equivalent transfer function of this full assembly, then we have to get a relationship between the net output y by net output x, which will be of course g1 x1 upon x plus g2 x2 upon x. Now, if once we are connecting them with a position like this, there essentially we have x is equal to x1 is equal to x2. That means that the same signal is being directed to both the components. So, it leaves us with g1 plus g2 to be equal to the net equivalent transfer function, that is g. That means, when multiple components are connected in parallel, then their equivalent transfer function will be the summation of their individual components. So, using this particular knowledge, we can clearly say that, like say for this particular assembly, our equivalent transfer function will be g1 into g2, whereas for this particular assembly our equivalent transfer function will be g3 plus g4, and that is what we have here, g1 into g2 here replacing the g1 and g2 individual components, and here again g3 plus g4 replacing the individual components. Now, we have another situation here which represents or which involves one feedback. Now, the idea of feedback is that, say, let me clean it again. Idea of feedback is that, let you have an input x being transferred to a component having transfer function g to get a net output y, but you want to control the value of x itself. Then this output whatever we are getting, this y itself is routed back to a feedback controller, generally denoted as h, corresponding transfer function, and supplied to this, where they may be connected by a suitable summation based components. So, x is being supplied here, and also a modified portion of y is also being supplied here, giving us this net. So, this one may be now become x1, and we are getting y as the output from this. Then what will be your x1? x1 will be equal to x, which is the original input, plus h times y. Then we are going back to the original component, that is this one, what its output is y, and what input it is sensing, that is x1, which is basically x plus h into y, that is giving us g. So, we are having y plus y equal to gx plus ghy. If we rearrange them, then 1 minus ghy is equal to g into x, which leads us to a net transfer function, if we represent that as g bar, which will be equal to y upon x as g upon 1 minus gh. Here of course, we have assumed that in this summation component, we have assumed that both signals are getting added to each other, but that may not be the case. Like you can see in this particular one, both are getting added to each other, but in this case they are getting subtracted from each other. If subtraction is there, then it will become 1 minus, instead of 1 minus gi, it will become 1 plus gi. So this way we can connect a feedback loop as well. Let us see what we have here. Okay, let me clear all this litter from here. So in this third step of modification, we have added the feedback components. Look at what we have. Now this G1 G2 combination has been added with H1 to get G1 G2 by 1 plus G1 G2 H1. Look at where you have the minus sign here, and which has led to this plus sign here. And also we have made another transformation. This particular component has been shifted to this particular part to make it easy. I would leave to you about how to calculate this H2 upon G5, just same algebraic modification that we can do. And now the rest part is quite easy. This whole thing here, we have G3 plus G4 and G5. So the equivalence of this one will become G3 plus G4 into G5, and that has a H3 as a feedback component leading to this particular one. And we already have this particular thing remaining, and this is the feedback from this, which leads to this final transfer function. So your input gets modified and to have this form output in terms of this transfer function. And now if we know all the expressions for each of these individual 8 components, then we have the final transfer function. So the concept of transfer function makes us very easy to combine different components of a measurement system in a single transfer function. And once we have the single transfer function, we can deal it with quite easily. There are several standard mathematical procedure. So today in the remaining part of this lecture, we shall be discussing about how to derive these transfer functions. But before that, we have to talk a bit about the standard inputs also. Once we know the standard transfer function of a particular component, then theoretically it is possible to subject that instrument with infinite number of inputs or infinite types of inputs, but it is not possible to standardize the response for each of such possible inputs. So what is commonly done is we test the response of a measurement system with known transfer function against some standard inputs, and then whenever we are dealing with an unknown or a different kind of input, we generally try to represent that as a combination of the standard inputs. Like we have already seen in the previous lecture, whenever we are having a periodic function to deal with, we can separate it into several harmonics component, and then the net response of the system should be the summation of the individual responses or the response to each of the individual harmonics. Similarly, there are a few other types of standard inputs also possible. Like this is the first one. Something like this we have already seen in the previous lecture. Here the input is 0 or constant till a particular instant of time, and then there is a sudden jump in the input, sudden change in the input to reach another constant value and remain there for rest of the time. This is referred to as a step input. So it is x equal to 0 as per the diagram here till t less than 0, and for t greater equal to 0 it becomes a constant. Now this constant can be positive or negative, means and also initial value this 0, it may have some other value also. Like the example that we have discussed in the last lecture, a thermometer was initially at a temperature of say 30 degrees Celsius, and now suddenly we take it to an environment having temperature of 90 degrees Celsius. Then this is being subjected to a step input. Instead of increase in value, we can also subject it to, suppose we take it in contact with a block of ice, then it has again been subjected to a step input, but instead of being an increase in the value, it is suffering a decrease in the value. Such inputs are called step inputs. Along with thermometer, there can be several other examples also. Let us say a very arbitrary example. You want to measure the mass of a pack of sand. So initially your measuring platform is empty, no load on this one, and now you suddenly drop this entire bag on top of this. So its load was initially 0, and now suddenly it is being subjected to a static load, a constant mass. If the mass of the bag is 50 kg, then suddenly the load on this one is increasing from 0 to 50 kg, and then that 50 kg is retained. So that what we refer as a step input. Next is the ramp input. Here it is the input signal is 0 till a certain time, and then it increases, but or I should say it changes, but there is no drastic change, rather it changes continuously with time following a linear path. This kind of inputs are referred as the ramp input. So, it is input is equal to 0 initially, and from t equal to 0, t greater equal to 0 onwards, it is a linear function of time where a is certain, a may be giving you the slope of this particular line. So, the ramp version of the examples can be thought about, say the example for the thermometer that we thought about. We initially you have a pool of water and your thermometer is being dipped into this pool. This is the thermometer bulb dipped into this pool, both the thermometer bulb and the water at the same temperature. Now, suddenly you take this assembly into a heater and started heating the water at a constant rate. Then we can expect the temperature of water to increase also following a constant rate, and hence the thermometer will be sensing a continuous change in its input value, input temperature value, something resembling the ramp input. If we talk about the pack of sand, instead of suddenly dropping the entire bag, we kept on adding sand on the measuring platform at a constant rate. We just cut open the bag, and then at a constant rate we keep on dropping the sand on this. So, that is like a ramp input. Both step and ramp are quite common kinds of inputs in practical applications that we get, and hence it is very important to test the response of any measurement system against these two inputs. Another one we can have is called an impulse. Impulse means, just think about that measuring platform again. Here we are not just drastically increasing the load by dropping a bag of sand, or we are also not continuously adding the mass. Rather, what we are doing, we are taking a hammer and striking the platform just for a very small fraction of time. Then what is happening, for a very small duration of time, it is being subjected to a very large amount of load. Before that instant there was no load, after that instant there was no load, but only for a very small duration of time it is being subjected to a huge amount of load. It is like, say, take the thermometer. Now you in somewhere you have a water kept at very high temperature. We just take the thermometer, dip it into the pool of water for a fraction of second, and then immediately take it out. That is something like an impulse input. For time less than that instant it was 0, for the next instant onwards again it is 0, but for a very small duration of time it will be infinite. Theoretically it is infinite, but there may be certain value for this. More about impulse input we shall be discussing in the next lecture, when we shall be subjecting systems to the impulse input. And the other one is the standard periodic input. As we can represent any periodic function as a combination of several sine waves, so we generally test any measurement system against a standard sine wave and test its response corresponding to the change in amplitude and change in frequency omega. So, that means this A and omega both are generally varied to test the response of the system, and accordingly we can extrapolate it for any periodic function. The response of a system against any standard input is generally referred with the corresponding name, like when we excite one measurement system using a step input, we call it a step response. When we use a ramp input, we call it a ramp response. Similarly, we call it impulse response, and when we are subjecting this by a periodic function, we generally call it a frequency response, the term which was already introduced in the last lecture. So, the first one in line is a zero order system. Zero order system is when the order of the system, that is that n that we have referred, is equal to 0. So, what will be the form for this? It will be a naught y is equal to b naught x. Here we are talking about n equal to 0, we are not putting any restriction on m. So, instead of having b naught x, we can have several other terms also, that is b1 dx dt plus b2 d2x dt2 and go on like this. But from our practical experience, we have seen that we never need to consider these higher order terms for the input. It is just this b naught x itself is sufficient regardless of what type of system or what order of system we are dealing with. So, we shall be restricting our input side only to this b naught x component. but on the output side we are taking a zero order system, that is we are putting n equal to 0, and once we are putting n equal to 0, then your transfer function, that is y upon x, will be equal to b naught upon a naught. This particular component b naught upon a naught is referred as the static sensitivity or steady state gain of an instrument. What it suggests or what it is looking like? It is just a static sensitivity is just a ratio of output to input, something very similar to the amplification or gain that we have talked about earlier. That is, the static sensitivity is nothing but an amplification in the output. It is giving a ratio of input to output to input, and if both x and y are time invariant, then what will happen? The static sensitivity reduces to the sensitivity that we have defined in the previous week. That is why it is drawn, this name is actually drawn from there. It represents the slope of a static calibration curve, and if the instrument is subjected to a steady state input, then it will also give you the amplification. This a zero order system is therefore is characterized by the static sensitivity, which is a measure of the amplification. It is the most ideal system that we can have, because here our transfer function is just a single k, it's just a one parameter k, none of the differential operator appearing, and so once we know the value of this k, the static sensitivity, we can easily correlate the output and input. And it is the simplest possible measurement system that we can have. There is no lag, no time lag between the input and output, means whatever input you provide, you will be instantly getting the output, and the value of input and output will be differing by this static sensitivity k. It is the ideal dynamic behavior that we expect from any measurement system. Like suppose if we are subjecting the instrument to a step input, this blue line represents the input, then depending on the value of the k, it is instantaneously going to give you the output, which is given by this red line. Depending upon the value of k, the output magnitude can be higher than the input magnitude or can be less than this, or if k equal to 1, both the red and blue line will superimpose on each other, but there is no time lag. That is, you can see here, as soon as you provide the input, your system is able to respond. It is immediately giving the output value, which is what we want, means we do not have to wait to get any measurement, we can get the measured value immediately. And by varying the value of this k, we can also amplify the signal, means we can increase it in magnitude or we can even reduce it in magnitude also to whatever range that we want. Even when it is subjected to some kind of periodic signal, just look at this. Here as the output, the red one again showing the output. In the output, we are again getting another sine wave having the same frequency, but maybe a different amplitude depending upon the static sensitivity of your instrument. So, zero order system is the most ideal system that we want, which is able to provide instantaneous response to your system. Like look at this case. Here there is no phase lag. If we are dealing with a zero order system and there are suppose three harmonics present in the input signal, it will not impose any artificial phase lag, the harmonics that you are going to get at the output. So, that is the most ideal behavior that we can expect. Something that very closely resembles the input is the resistance based displacement sensor called the potentiometer. In the concerned module, we shall be discussing a bit more about potentiometer, but the principle of potentiometer is that here you have a resistance like this, which is being subjected to which is being excited by a constant voltage source kept here. Let us say the height of the resistance is this xi, or say x1 is the original height of the resistance, and the displacement that you want to measure or the displacement of the device of the system which you want to measure, that is being connected with this particular needle, and this needle, as the system is moving, this needle keeps on moving up and down along this resistor. So, as the system is moving up and down, accordingly the voltage available at this side, that also will keep on varying. And suppose if the total resistance, if resistance we take as proportional to the length of the resistor, then x1 is the original length, and at a particular instant of time, your indicator is connecting this x2, then if E is the voltage that is being imposed and small e refers to the voltage, or small e naught is refers to the voltage that your indicator is showing, what will be the ratio? It will be the output is E naught, input is capital E, that will be a straightforward relation between this x2 and x1, that is a straight line relation, that is a perfect zero order instrument that we can get. Instead of being such a linear scale, sometimes we can also use an angular scale to measure the angular displacement, but regarding potentiometer we shall be talking about a bit more. Another system, which another very common system which you already know about, which is also quite can be thought about as a zero order system, can be a spring gauge, which or a spring balance, I should say, a spring balance which we generally use for measuring the weight something. As the system or the measure end is connected to the hook of the spring gauge, immediately you will find a deflection of the spring indicating which will cause the deflection of the indicator on a which will move on a scale, and you get the measured weight or weight of the measure end directly from the scale. That is also quite close resemblance of a zero order system. But practically there may be several issues for each such examples which may limit the zero order behavior. Like in case of potentiometer, there can be several issues which can force it to deviate. One can be the here to measure this E naught, we have to connect some voltage measuring instrument, maybe a voltmeter, maybe an oscilloscope, which is going to show the output. Now that itself requires some current for its own operation, and therefore it is going to make some change in the value of this E naught itself, thereby causing some distortion in the final or some change in the final output. And then secondly, the resistance that we are talking about here, this resistance we are representing by the in terms of its length, but that is true only for a pure resistor, and there is nothing like a pure resistor in nature. Every resistor will always have, whatever small may be, some inductance and some capacitance associated with this, and those inductance and capacitance will lead to some amount of voltage leakage from this. Another very common reason, the indicator of this particular indicator which is moving over the resistor, that itself may suffer from mechanical friction, that may have some contact friction associated with it, may have some inertia associated with it. Means once the system suffers some displacement, the indicator itself may take some time to move over the indicator, move over the resistor rather, and so those lags, those mechanical lags, mechanical friction will also cause some change or some distortion in the final value, and all such reasons may force the potentiometer or any such zero order instrument to deviate practically from the ideal zero order behavior. But still, zero order instrument is the most preferable one for any kind of measurement. Unfortunately, we have very few examples for zero order instrument, but there are several examples of a first order instrument. So, for a first order instrument now we have n equal to 1. So, if we go back to our original equation, what we have, our equation now is a1 dy dt plus a naught y is equal to b naught x. Remember, we are not taking any term after the first one on the right hand side. So, going back to our differential representation, we can write it as a1 d plus a naught into y is equal to b naught x. So, we have three coefficients to deal with, a1, a naught and b naught. All other coefficients are 0 for a first order system. Truly speaking, we do not need three coefficients. We can always divide the other two by any one of the coefficients, thereby reducing the required number of parameters to just 2. We can either divide everything by a1 or a naught, but just to be consistent with what we have done for zero order system, let us divide everything by the a naught. We are dividing everything by this a naught. So, if we divide everything by a naught, we have a1 upon a naught d plus 1 y is equal to b naught upon a naught into x. What is b naught upon a naught? we have already seen for the zeroth order system, that is the static sensitivity or steady state gain. But we are having a new term here, this A1 upon A naught. A1 upon A naught, what do you feel, what will be the dimension for this quantity? Okay, before that, what is the dimension of your static sensitivity, that is this K. Static sensitivity from the, if we just go think about the zero order instrument itself, there K, which is B naught upon A naught, is directly your Yt upon Xt. So, the unit of K will be your unit of the output by unit of input. Like if you think about say one thermometer, liquid in glass thermometer, there your output is the displacement of mercury inside the column. So, Y will be having a unit of meter or some corresponding length scale, and X is the input, which is the temperature, change in temperature. So, it will be say degree Celsius or degree Kelvin. So, output to input, whatever is the unit, the same will be the unit for this K. But what about this quantity A1 upon A naught? Look at this particular equation carefully. A1 upon A naught, whatever may be the nature of your X and Y, you will always find this. Okay, once more, you just take a look. Here you have one involved here, which is a dimensionless quantity, and you have a differential operator involved here for this. So, if you look at carefully, your this A1 upon A naught will always have a dimension of time. We shall be seeing one example maybe in the next slide. And that is why it is often referred to as a time constant tau, which gives a measure of the speed of the system response, and accordingly we can represent this first order system as tau d plus 1 to y is equal to k into x, or this is the corresponding form in transfer function. K upon tau d plus 1 is the transfer function for a first order system. It is different from the zeroth order, because here we have a denominator involved and we can't have just a straight one to one correspondence between output and input. Rather, we have one differential operator involved in this D, and also like in zeroth order system there is only one characterizing parameter in form of static sensitivity. Here we have another one to deal with, which is this time constant. So, time constant, I repeat, gives a measure of the speed of system response, and it is always desirable. Okay, let us wait to see whether we want a larger value of tau or a smaller value of tau. We shall be seeing through some examples. Now, example for first order system, there are several. Most common one is a liquid in glass thermometer. There can be other examples like one capacitor discharging current through a resistor. There can be one tank of water leaking through a valve. These are all very common examples of first order system. We shall be seeing a few more examples later on. Let us just concentrate on this one. You have or we have a common thermometer which is being dipped into a pool of water. Let us perform an energy balance over the bulb of the thermometer. Now, if we think about the thermometer bulb, say this is your thermometer bulb, maybe a very bad drawing of that. So, this is the bulb, the hashed portion. This bulb may be having a volume VB and it is having a surface area of AS. So, valve is having a volume VB and a surface area of AS. Then what it is doing, if whatever may be the initial temperature, if that is different from the temperature of the water, surrounding water, then it will experience some heat exchange. So, let us assume that the surrounding water or surrounding fluid is at a higher temperature, then heat will be flowing into this. What is the mode of heat transfer here? Correct, it is convective heat transfer, and the result of this heat transfer will be a change in the total energy content of the fluid, the thermometric fluid here. So, using this, let us write an energy balance for this thermometer bulb. So, how much energy that is being supplied in the form of convection, that will be U, which is the overall heat transfer coefficient, into the surface area, which is this AS, into the T of the surrounding fluid, let us say T infinity refers to the surrounding fluid, minus Tf refers to the thermometric fluid. both can be function of time. Of course, T infinity itself can be a function of time, and the fluid temperature Tf definitely is a function of time. Let us neglect any heat loss from this. So, this is the amount of heat addition, there is no loss. This entire quantity will lead to a change in the energy content of the system. Now, how we can calculate the energy content of this, or how much is the energy change in this energy content? Let us perform this energy balance over a small interval dt. Then this is the total amount of energy that has been received by a thermometer bulb minus there is no loss. And if this over this small period of time dt, let us say there is dTf amount of change in the temperature of the thermometric fluid, maybe mercury, then how much will be the change in total energy content? That will be the mass of the thermometric fluid, which is rho into Vb into its specific heat into the change in its temperature. This here C is the specific heat, rho is the density, both corresponds to the thermometric fluid, Vb as we have mentioned. And so, we simplify this. So, we have UAS T infinity minus UAS Tf is equal to rho Vbc to dTf dt, or write in more formal way rho Vbc dTf dt plus UAS of Tf is equal to UAS T infinity. Remember, T infinity itself can be a function of time. So, how this equation is looking like? Very similar to a first order equation, like here this one is your A1, this one is your A naught, and this one is your B naught. T infinity represents the x, Tf represents the y, and time is a variable for this. But think about the thermometer itself. Our output, is it coming in terms of Tf? Because actual system output is coming only in terms of expansion of the fluid through the capillary tube. So, we have to somehow convert this Tf to the expansion of the fluid in the capillary tube. Let us assume that when Tf was equal to 0, all the mercury or all the fluid was restricted inside the bulb, and so there was the length L of fluid column in the capillary, it was 0. As Tf keeps on increasing, L also keeps on increasing. Then how can we relate this Tf with L? If of course the length, or let us write say at a certain instant of time, if L is the length of this thermometric fluid column in the mercury, what is the volume of that? Its volume is definitely L into cross section area of the capillary. Here AC refers to the cross section area of this particular capillary. So, L into AC is the total volume inside the total volume of mercury that is there inside the capillary. And from where this has come in? This has come in because of the thermometric or volumetric expansion of mercury which was there inside the bulb originally. So, if beta refers to the volumetric expansion coefficient, then beta into the original volume Vb into Tf, that gives the relationship in between L and Tf, or we can write Tf to be equal to AC upon beta Vb into L. So, let us replace this one in the earlier equation. So, if we go back to the earlier equation, then we have rho Vbc into, from here we can also write that dTf will be equal to AC upon beta Vb into dL. So, putting it there, we have AC upon beta Vb into dL dt plus original equation at UAS into AC upon beta Vb into L, of course, is equal to UAS T infinity So, the original equation we have now converted in terms of Tf, it was there, now we have converted that to the terms in terms of L, and L is the output and T infinity is the input. And now if you divide everything by your A naught, that is this quantity, then what we are going to get? We are going to get rho VBC divided by U AS, that is going to be equal to dl dt plus L will be equal to beta VB upon AC terms of T infinity. So, what we have? This is the final equation, just written in a much clearer fashion. So, this one, what is this one? Beta VB by AC, this is the static sensitivity or steady state gain, and this rho C VB upon US, it is what? It is the time constant for a system. Of course, while so we have a situation of a first order system where we already got the expression for both static sensitivity and the time constant, and once we know these parameters, like you can just look at this, VB, AS and AC are geometric parameters. VB refers to the volume of the bulb, AS is the surface area of the bulb, and AC is the cross section area of the capillary tube. So, once you are having the thermometer, you have all this information known. Rho, C and beta are properties of the fluid that you are using, mercury or whatever. So, those are also generally well known, and only problem is with this U. U is the overall heat transfer coefficient. Now, U may depend on the surrounding or generally depends on the surrounding. Like if the thermometer is dipped into a stagnant pool of liquid, whatever will be your heat transfer coefficient, if it is dipped into a flowing field of liquid, then we can expect U to be much higher. And also if it is dipped into, instead of liquid, if we keep it in air, then U will be much lower. So, U is not truly a system parameter, we need some information about the surrounding as well to get a measure of U. But like in case of zeroth order system, there are also several factors which may cause the first order system to deviate from its first order behavior. Like there are several assumptions we have already taken in this derivation. First, we have neglected any heat storage capacity of the wall material, like the glass. We have assumed that that is not storing any heat, and also there may be a small film of liquid out on the outer side of this, and also small film of thermometric liquid on the inner side of the bulb. We are neglecting the heat storage capacity of those. We have assumed U to be constant, but truly speaking U itself may be a function of temperature, because properties of the fluid, both thermometric fluid and the exterior fluid, both can vary with temperature. We have neglected the expansion and contraction of the bulb. That is not a bad assumption, truly speaking. Like glass kind of material has a very small expansion coefficient and generally are negligible as long as the temperature change is limited. We have neglected any heat conduction along the stem to the upper side of the capillary tube. Again, if we choose a material with very low thermal conductivity, this is not a bad assumption. Constant mass of fluid inside the bulb that we have assumed. Whenever there is an expansion taking place, some fluid is moving out of the bulb. During contraction, some fluid are moving back into the bulb, but if the diameter of the capillary is very small, then the amount of mass that goes out of the bulb, that can be very small, almost negligible. And finally, we have assumed the fluid properties to be constant. So, with this we have got these two expressions for K and tau. Just look at this, what will be the unit for this K and tau? We will do this unit calculation from the right hand side. Beta is the volumetric expansion coefficient. What is its unit? Do you remember? It is rate of change of volume per unit temperature. So, its unit is 1 upon degree Celsius, where we are sticking ourselves to Celsius as the unit for temperature. VB is volume, so it is meter cube. AC is area, so meter square, giving the unit of this quantity to be meter per degree Celsius. Like we have discussed earlier, meter is the unit for your actual output, which is length. Degree Celsius is the unit for your actual input, which is the temperature of the exterior fluid. Come to the time constant. Here you have rho. So, rho is SI unit is kg upon meter cube. C is specific heat. So, it can be taken as joule per kg degree Celsius. Then you have VB upon AS. VB is meter cube upon meter, and U volumetric expansion coefficient watt per use the overall heat transfer coefficient watt per meter square degree Celsius. As we are already having a joule left, so instead of watt we write it as joule per unit time. Now look at this. So this meter cube goes off, here we have a meter square, this corresponds to the AS. So the meter square goes off, degree Celsius, joule and also kg goes off, leaving only this second, which is the time constant for this. And also another thing we can look for, if we want to increase the sensitivity of your thermometer, what we have to do? Firstly, we have to choose an instrument which is choose a fluid which is having high beta, and we also have to design it such that this ratio Vb upon AC, okay, Vb upon AC will come not into picture. We have to ensure that the volume of the bulb is high and the cross section area of the capillary is very small. Similarly, if we think about time constant, if we want high time constant, rho c should be high, rho c product, again Vb should be high and surface area should be low, whereas heat transfer coefficient again it should be as low as possible. So a high value of Vb gives us high value of K and also high value of tau. High sensitivity is always desirable, but for time constant we do not know yet. Let us check it with respect to one standard input. In certain situations, however, the effect or the parameters, the way they affect K and tau, they may be contrary to each other. So we may have to go for certain kind of optimization to identify both high sensitivity and favorable time constant. So first we check the step response. We know this is the step response. So how to do it? We know for a first order system, this is the way, this is the standard form. Here K is the static sensitivity and A is the input that we are giving for any value of tau, or any value of time greater than 0. So we have to solve it. Any ordinary differential equation of this kind, where we can find the solution in two parts, one is called the complementary function, other is a particular integral. So if I am just directly giving you the solution, if we solve it, for in this particular case the complementary function for y will be some constant c into e to the power minus t upon tau, whereas the particular integral in this case will be the right hand side itself, the Ka. So the actual solution for y will be a summation of these two, that is c into e to the power minus t upon tau plus Ka, but c is an arbitrary constant. So we have to get the value from our boundary conditions, or I should say initial conditions. What condition we know? We know that at t equal to 0 your y is equal to 0. So if you put this value, 0 will give you c into e to the power 0 plus Ka, leaving to us c is equal to minus of Ka. So we put it together, final expression for yt comes to be equal to Ka into 1 minus e to the power minus t upon tau, which is this, where K and tau are the properties of your measurement system, A is the amplitude of the step input that you have provided, and t is the time variable which changes from 0 and can go to infinity. You can clearly see there are two parts of this solution. One is this 1 which is a constant value, and other is this particular quantity. We can explain it a bit more if we represent the solution in this form. Here we are dividing the output by K into A, thereby making it non-dimensional. Look at this, here this term is 1 which represents a constant, and what about this term? This is an exponential term, a negative exponential term. So when t equal to 0, this term goes to 1, giving leading y equal to, or I should not say y, giving the left hand side, that is y upon k into A, to be equal to 0. But when t tends to infinity, then what happens? Then this exponential term goes to 0, leaving this to be equal to 1. That means this actually is a measure of the error that can be present in the system. As we move with time, this exponential term, this error that keeps on reducing, and for a very long duration of time this goes to 0, thereby giving ideal response from your measurement system. This is one example where we have taken k to be equal to 1 and tau equal to 0.5 second. Just see here, the blue line is the input, your step input, the red one is the output that we are getting. You can see, like in zeroth order system, we are getting an immediate response which we are not getting here. Of course, the system start to respond from this point itself, but it will take some time to reach the actual signal. Theoretically, it will require infinite amount of time to reach the actual signal, and so its rise time, I hope you remember the rise time. Rise time refers to the time the measurement system reaches to match the input value, or this y upon ka quantity, the time it requires to reach this value of 1. Theoretically, it is infinite, but practically instead of rise time we use the settling time. Settling time means the time the measurement system requires for this output signal to reach within certain band, say within 5% or 10% of this value. Like if we take a band of say 90%, then we are talking about this y upon ka value to be greater than 0.9. Once this y upon k value becomes greater than 0.9, we can say that the output has reached within 10% of your desirable value. Let us say if this is the time, if this is the range, then we can say this is the point where your system enters that band. So, this particular period can be referred as your settling time. But let us now check what can be the effect of your time constant. Here we have compared 3 different time constant. The continuous red line is the same when this particular line refers to tau equal to 0.25 and this particular line refers to tau equal to 1. What we can see there? As the time constant is increasing, system requires more time to reach the actual output, or the settling time keeps on increasing. That is why it is always better to have a system with smaller time constant. That is logical also, because time constant gives you the speed of system response. Smaller the value of time constant, higher is the speed of system response. So, we always prefer a system to having a smaller time constant. Now, if you just refer back to the example of thermometer earlier we have used, there we have seen that when the VB increases, sensitivity increases, but time constant that also increases. Therefore, we may have to go for some kind of trade off, because higher volume of this bulb will give you higher sensitivity, but at the expense of lesser time constant. And time constant is very precious, because we can't wait infinite amount of time to get your output from the system. The measurement error is often referred as the input minus this y upon k quantity. So, in this case it will be a into t to the power minus t upon tau, and if we plot that with time, you can see that initially your measurement error is 1, which is referring to this particular point, and as the time goes on the error keeps on reducing. So, again if we are sticking to a 90% band, then we can allow a maximum of 10% error in measurement. Then something here somewhere if 0.1 value is here where the system enters that band, and so from this point onwards we can take the reading. Like just think about how is the clinical thermometer. We take it and put it in contact with our body, but we do not take the reading immediately, rather we wait for some time, and we take the reading after say 1.5 minutes or 2 minutes, because it has a certain time constant. It requires certain time to enter the allowable error limit, or for this error to become smaller than the allowable value, and then only we take the limits. Higher time constant is not desirable. We always prefer an instrument with a smaller time constant. We shall be checking another response today, that is the ramp response. We know this is the form of the ramp. So, this is the corresponding functional form, and if we solve this one following again the complementary function and particular integral, we are going to get a solution of this particular form, where we again have two parts, both cases the tau is involved, and check out the measurement error. Then we are having a form like this. Now, look carefully here. In the error, in the previous case we had only one part, which is an exponential term, a e to the power minus t upon tau with step input, but here we are having 1 minus that. This term of course as time goes on, this one goes to 0, but what we are left with when this tau, when your time t tends to infinity, your measurement error will become a upon tau. That means it attains a constant value. That means in case of ramp response, your system will always have some constant error, which is often referred as a steady state error, and it will never be able to reach the actual input value. As the input keeps on increasing, the output will keep on following that, but with a constant gap. Just follow this. Here again the blue line is the input, the red one continuous one is the output. So, in the initial period, over some period somewhat like this, the nature of the output also keeps on changing, but once it reaches this, you can see here there is a consistent gap that is maintained between input and output, which is this a tau quantity, this steady state error. The system will never be able to recover this error, rather you will always have, as long as the input keeps on increasing, output will keep on following it, but with this amount of error. The dotted line is something with a different time constant, again a different time constant, higher that smaller the time constant value, lesser is the amount of error in this case. So, this is the corresponding error. You can see the error initially is 0 here, and then it keeps on increasing and then becomes constant beyond a certain time for this. So, these are step and ramp response. We shall be talking a bit more on them in the next lecture, and we shall also be checking out the response of a first order system in terms of impulse and frequency response, and then we shall be moving on to the second order system. So, just to sum up what we have learned today, we have talked about the generalized representation, we have developed the generalized mathematical model, then transfer functions was introduced, and we have also seen how we can combine transfer function, and then we have talked about different standard inputs, step, ramp, impulse and frequency input or periodic input. Then we have talked about the zeroth order sensitivity, which gave the concept of static sensitivity, zeroth order system, which gives the static sensitivity as the characterizing parameter. Then the first order system introduced the time constant, and then we have discussed about the step and ramp response of first order system. So, in the next lecture, which I am expecting to be the last in this week, we shall be discussing a few more examples of first order system, the response of first order system against impulse and periodic inputs, maybe solving a few numerals, and then we shall be talking about second order system. Generally, we do not have to go beyond second order system, because all common measurement system can be classified either as 0, first or second order system. So, that is it for the day. Thanks for your attention. We shall be back soon with the next lecture of this module. Thank you.